Starting to talk about trigonometry, and we have two or three more units of like the calculus part of this course, and then we move over to the vectors for a couple of units at the very end of the course. But everything in the calculus, I mean, it all has to do with derivatives. I'm sure you've gathered that by now. That's the foundation of calculus, the idea that we can take derivatives and do interesting things with them. And so we're just kind of, for every one of the units that remains, if we're looking at a new type of function, like we'll look at logarithmic functions and exponential functions eventually. And the first thing we look at is how to take the derivative of that type of function. And they're all very different. So that's what we have to do before we can do any work with the trigonometry, is how do we actually take the derivative of a trigonometric function. Okay, that's what we have to determine first. And then we'll start to answer questions with that. So it's not quite the same as polynomials or as rational functions. We've proved laws around how we could take those derivatives. With this, we're just going to do it by inspection. We're going to kind of look at what's happening in the graph and see if we could just look for a pattern, notice something. Remind me what the derivative of a function is. This is it's what it always boils down to, and we lose sight of this sometimes because we get into the algebra of it and just doing questions. But what is the actual derivative? It's the slope of the tangent. So can't I eyeball the slope of the tangent and work backwards to kind of figure out what it is? So at this point here, what's your guess at what the slope of the tangent is? You might try to draw a tangent on your page, just lightly. You don't want to muck it up too much, but try to draw a tangent and see if you can figure out what the slope would be. It does look like 1, and it is. So if I draw a tangent line there, mine's terrible, but if you have a ruler and you can do a better job, you'll notice that it's positive 1. So what would we do? We would plot a point there. What's another place that I can easily find a tangent? Yeah, and what is it there? So at this point here, the tangent is 0, which means I'll have a dot there. What about here? What do you think it's going to be at pi? Yeah. And then again here, it's going to be 0. And then again here, it's going to be 1. So just looking at those, what do you think? It does look like cosine. Now maybe it's just like an absolute value, but I don't think so, because it's not going to keep going up there, right? And here's something that's interesting here. So let's look at this a little bit more carefully. And we can see this is the equation of the tangent. So the slope will be in there. So it is 1. And if I drag it, we can see that the slope is, like, this number is not important, right? But this number is. So the slope is getting, it starts at 1, and it's getting smaller, 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 and then it's going to 0. And we notice that it's not changing very quickly here, and it is changing quickly there. So we could use this and kind of deduce and figure it out, but with technology it's kind of nice. So I can actually turn this trace on. And what it will do is, as I drag it, it'll plot. That's the slope of the tangent, right? The y value of that is the slope of the tangent. We see that it started at 1. And so as I drag it, it'll actually trace all of them and take a look at what happens. As long as I don't go too fast. Yeah, it's cosine, isn't it? Very interesting. There you go. So we'll draw that in there. Okay, I want you to just quickly try to do the same thing for cosine. You might think if the derivative of sine is cos, then the derivative of cos would be sine. In a perfect world, that might make sense. I don't know. There's an interesting kind of symmetry to that, but it actually turns out that's not quite right. If you just think about, like the first point is 0, right? When we start at 0 cos, the slope of the tangent there is obviously 0, and it's 0 here, and it's 0 here. So those are points that we can get. And if I go to this point right here to figure out where it is, I notice that it's sloping to the negative, right? So, so I would have 0. What happened there? 0, 0. This is not cooperating. Oh, there we go. 0, 0, 0. But here, it's actually sloping to the negative. So this is going to be at -1, and this is going to be at +1. So what is that function? See, this is important, and this goes back to MHF, like recognizing equivalent trig expressions. How would you define that function? Very nice, negative sine x. And if we go here and take a look at this, I think this is going to work. The slope of the tangent starts at 0 and then goes into the negatives right away, -1, and then goes back towards 0, and then +1. Very nice. And if I go back this way, it continues on. And of course, we know because of the way the cosine and sine functions work, there's other ways that you could call it. Like there are other functions that we could call that. But negative sine is what we use. Okay. Whoop. So, to summarize, if y equals sine x, then y prime equals cos of x. And we're going to write this in a different way. I'm not sure. You might have seen this in the textbook, or if you ever looked anything up online. This is a standard way that we talk about things. I'm not sure if we've used this notation quite the same. We do this. D something by dx. So like normally it's dy by dx, right? But y is just equal to whatever expression that we're talking about. So we can actually put expressions in here. So this is sometimes a way that will show what the derivative of something is. And then you will believe me when I say this. So the reason why it's sine of u is some expression, probably in terms of x, wouldn't necessarily have to be, but that's the idea. So if it's more complicated, okay, then it's cos u times the derivative of u. So that's like kind of like the chain rule applied to trigonometry, right? Where you take the derivative of what's inside. Okay, and then if y equals cos of x, y prime is negative sine of x. And we can do the same thing. Same thing there. Okay? So we haven't proven this, but it's pretty clear, especially with the demo with the technology. It's pretty obvious that that's what's happening. And now we've stated it. It is true. So there we go. Any questions about that? Pretty important to know. Make sure you don't forget that. Don't get that mixed up. Don't get them backwards. Don't get the negative sign in the wrong place. Oh my goodness. Like, this is the most important thing that you could learn from this whole unit, right? Is that. So don't get to the test at the end of this unit and make that mistake. Okay, let's start applying it and do a little bit of work with this. Some easy ones to start, and then they will get more interesting. So the derivative of sine is cosine. So cos of the same angle times the derivative of what's inside. And typically we'd write it this way. 3 cos 3x. We get caught up in the algebra. But don't forget what that is. That's an expression that you could plug any value in for x, and you get the slope of the tangent at that point on the original curve, right? Like, remember what that function actually is, what that expression gives us. Okay, let's try another one. Okay, so we've got 8 times negative sine of 4x times the derivative of what's inside, which is the 4x. So that's 4. 8 times 4 is 32, so negative 32 sine 4x. And you wouldn't typically take 2 lines for that, but just to show it clearly while we're getting warmed up, trying these for the first time. Easy enough? Any questions? I would say it's a little bit strange at first, or a little bit tricky at first when you start to do these with exponents. So this is like sine x all to the 1/2, right? So you got to break this down, and I think it's really important, like the work that we're going to do derivatives for just a couple of days. So today and tomorrow we're going to do more practice of this, but these are pretty crucial days where you want to get very good at this so that you're not struggling later on. And it's, like I said, I think it's strange at first. So y prime is 1/2 times sine of x, subtract 1 from the exponent, and then multiply by the derivative of what's inside those brackets, right? It's the same as how we would do it, which is cosine of x. It's the same as if we had the square root of x cubed. That'd be x cubed to the 1/2. So we'd take the 1/2 out front times x cubed times x squared, right? Like that's how you would do that one. So it's the same idea. You can relate it that way. And then if we clean this up a little bit, we're going to get cos x over 2 root sine x. You want to try the next one on your own? Again, that notation means cosine of x all to the 5th, right? We write it cos to the 5th x, or cos squared x is the one that we're more used to, but that's what it means. So what's this one going to look like? It should look like this. Cos, that's the start of it, right? Bring the exponent out front, multiply, subtract 1 from the exponent, and then multiply by the derivative of what's inside. And by that I mean like the derivative of what's inside these brackets. So that's times negative sine x. And we would probably end up writing it like this. Negative 5 sine x cos 4x. Questions? We good? All right, we're just going to keep going. Get as many of these done as we can. The more complicated they get, the easier it becomes eventually to do all the different kinds because we start to see it. And I think we'll see this in a question coming up, but as is, well, true with a lot of things, but with trigonometry, you know, there's different ways that you could write your solution, and so how you will do that really depends on what you're doing next. So if you're just taking the derivative, I mean, we typically want to clean things up a little bit, like putting constants together or monomials together, that kind of thing. But some of the stuff we do will be a matter of preference or choice for now, at least. But I think some people would have questions about like, oh, when would I factor? When would I do this? When would I do that? That kind of thing. And right now there is no answer. Okay, so let's take a look at this one. So I take the 4 out. I'm going to multiply it by the 7, and I get 28 sine cubed of 5x cubed times the derivative of like what's inside from the first part, which is cos of 5x cubed times the derivative of the angle, 5x cubed, which is 15x squared. So there's like 3 layers to that one. And this is what I mean by cleaning it up. Typically, you would take these monomials. So 15 times 28 is 420x squared times sine cubed of 5x cubed times cos of 5x cubed. Good? Do you follow the steps that happen there? So again, here, let me do this. I thought about it like this. 7 times sine of 5x cubed all to the 4. This could be anything. And it would be 28a to the 3. Right? But then a is a derivative and we're going from there. Everybody okay with that? All right. Again, why don't you give this one a try? Did everybody get that to start? And then that's the second part of it. Are we good with that? If somebody wasn't paying any attention or didn't practice and you know, really nail this, we start to see signs popping up here instead of here, right? Like people change that to a sine, forgetting that there's supposed to be a cos part. Like it's interesting. We're going to clean this up a little bit, but it's interesting how we started with such a simple idea. You couldn't be more simple. The derivative of sine is cosine. And then we get these, pretty quickly we start to get some pretty sort of nasty expressions, right? Like there's a lot going on in these. And look at this one. Oh my gosh. Right? It gets pretty complicated pretty fast. So there's a lot of places where somebody could make a mistake. Okay, so I'm going to, and again, this is where like there's no rule for what you would do. It depends on what you're doing next. But I noticed that there's a common factor in that last binomial there. So I'm going to pull that, I'm going to pull a 4 out. Pull it out front. And 60 times 4 is 240. And then the rest I can't do much with. So I'm not saying you have to do that. And I'm going to put the negative out front there. Oh, that's wrong. X minus 1. It's fairly standard, just scrolling back up here, that when I have something like this, we don't put brackets around the angle. We often drop that. I don't know how much of that we did in MHF. Sometimes we probably did, but now we really start to. But obviously when you have an expression like that, it's got to be around brackets because otherwise you wouldn't know where it ends, right? So be careful of that. All right. Anybody have any ideas on how we could figure out the derivative of tan x? All the stuff that we did in MHF is going to start to come in handy pretty quickly. How could we explore this? Do it the same way, draw a graph of tan x? We could, but make somebody think. I think that makes a lot of sense because we know how to take the derivative of sine and we know how to take the derivative of cos, and we know how to take, use take the derivative of quotients, right? Something over something. We've got rules for that. So absolutely. The quotient law. The derivative of the top is sine x, so the derivative of the derivative of sine is cosine. So cos x times the bottom minus the derivative of the bottom, which is negative sine x times the top, all over the bottom squared. Straightforward enough, right? Cos x times cos x is cos squared x. Negative times negative is positive. Sine x times sine x is sine squared x. What do we notice? The top is 1. Pythagorean identity, very good, right? This is what I'm saying, is that all that stuff we did in MHF, all the identities, I mean, that one's from grade 11 anyway, but so 1 over cos squared x, or secant squared x, which is often how we think of it as secant, but secant is 1 over cos squared, so, we can use those more or less interchangeably. Okay, so let's just write this out. The derivative of tan of something is the same thing. It's secant squared u times the derivative of u. And we could show this the same way, but we're just going to give you this one. Any guesses to what it might be? Yeah, cosecant squared, right? So it would be the same thing because it's going to be like cos over sine, so that it's going to work out. And it turns out it's negative. Cosecant squared u times derivative of u. Okay, very important. Everybody get that down? I didn't go too fast. You get it? Okay, let's try a few more. Go ahead and do that one. This one's pretty straightforward. Anybody tell me what it is? Andrew, what'd you get? 8 sine x, and then no, times cos x. Good. Don't forget to do that part, right? So that's like, let's see, you've done this part, sine x all squared. You did this part, 2 times 4 times that, but then times the derivative of what's inside as well, right? Good. Now, here's where, like, there's no rule necessarily, but this is where we start to notice things, and it's a good idea to start trying to notice these things. And I don't know, as you're working, your answer might not match the answer in the back of the book. And if that happens, I would say it's a really good idea to think about why and explore that. Ask a friend or come in and ask me. Don't just look at the solutions online. Try to figure it out yourself. But things like this, how could I rewrite this? I could rewrite this as 4 times 2 sine x cos x. Does anybody recognize 2 sine x cos x? No, but you're on the right track. But this is from a while ago, so it's the same as 4 sine 2x. So sine 2x is equal to 2 sine x cos x. Remember that one? That identity? Now, I don't know why we want to write it like that. This is my point. There's no reason, there's nothing in this question that leads me to believe I should rewrite it that way. If I left this question on a test as 8 sine x cos x, that's fine. But maybe there is some reason, like maybe there's something else you're doing further in the question where you would want to. So what I'm saying is it's kind of nice to start recognizing identities and thinking about those kinds, getting back into that mindset. Okay, so this is just the derivative of tan, which is secant squared 5x times the derivative of what's inside. Derivative of 5x is 5. So 5 secant squared 5x. Or, again, it would be 5 over cos squared 5x. But we'd normally probably leave it as secant. We good? Questions, questions, questions. We got a few more to do. Keep going. I want you to try this one. Well, I'm going to give you a heads up. It's the product rule. And I believe it's the first one we've seen that's like this. It's kind of a simple product rule, but we did one with the quotient. But this is a product rule, right? So how do you do the product rule? All right, very good. Lots of people. So f prime, the derivative of the first thing is x. This is x times tan of x. So the first thing is x. So the derivative of the first thing is just 1. So it's 1 times tan of x, which is just tan of x, plus the derivative of the second thing. So that's secant squared x times the first thing. And that would be better to write x secant squared x, but really either way. Okay. All right, now we got a couple of questions where we're going to actually do something with it. Find the equation of the line. What do we need for the equation of a line? Back in grade 9, this is how we think about equations of lines. This is a tricky unit in grade 9. It's the first time you're really getting into this kind of algebraic stuff. Oh, sorry, I'll leave that up, copying it down. But this is how I try to frame it. And this is great for all kinds of algebraic processes. Y minus y1 equals m times x minus x1. So this is a formula. Every formula has inputs and then an output. The output is whatever it gives you when you use the formula. So Pythagorean theorem formula, what's the output? A side length. What's the input? 2 other side lengths. What's the input for this formula? What do I need? And this is what I'm saying. This is a good way of thinking about any problem solving, any formula. A lot of them are straightforward, but whether it's area of a square or volume of a cylinder or whatever it is, what are the inputs? Like, what do I need in order to use this formula? Slope and a point. If I write down the formula and just think about what it looks like using it, I think, okay, the things that I need are I need a slope and I need a point. Do I have either of those things right now? I do not. What do I have? So eventually I need to have m equals something and then x, y, that's a point, equals something. And I don't have most of that. All I have is an x. So I got to find the m and I got to find the y before I can use the formula to do what I'm asked to do in this question, which is find the equation. So I got to go do some work to find those 2 things. Finding y should be easy. Y equals cos of x when x is 5 pi over 6 is y equals cos of 5 pi over 6. What is cos of 5 pi over 6? Now we got to go back and start evaluating this stuff. So very quickly, 5 pi over 6 is in which quadrant? It's not quite 6 pi over 6. 6 pi over 6 would be here. So it's a little bit back from that. So we're in quadrant 2. Cosine is negative there. What is cosine of pi by 6? No. 1. Oh, it might be close to 1, but let's get an exact value for this. That doesn't seem right. Is it? Maybe it is. This is how I think about it. I always remember that cos of pi by 3 is the special one. It's a half, right? Like that's the one that's nice to memorize because you can check and make sure your calculator's in the right mode. I wonder if your calculator's in degrees. Mine is. I'm going to switch it. Oh, how do I do this? Setup, degrees, gradients, radians. So I'm going to switch it to radians. I'm not going to take the cos of pi by 6. I'm going to take the cos of pi by 3 to check that my calculator is in the right mode, 0.5. And when I remember that it's 0.5, then I remember that one, and then I remember pi by 6 is the other one, right? And again, this would be from this triangle, special triangles, all this good stuff. Now it's all flooding back to us. So pi by 3 is the big angle, and it's 1 over 2, and the other one's root 3 by Pythagorean theorem. and this is pi by 6, and this is pi by 2. That's a little bit hard to read, but it's there. So cosine of pi by 6 is adjacent over hypotenuse, which is root 3 over 2, and it's negative. So, whoops, don't want it to be green. So it's negative root 3 over 2. There we go. So all of that was just to get this. I still need m. How am I going to find m? Got to have something to do with calculus, don't you think, since this is calculus class? We're looking for the tangent line, the equation of the tangent line at that point, so that we need the slope of the tangent, which is the derivative, so we're obviously going to take the derivative. So y prime, the derivative of cosine is negative sine. And then at x equals 5 pi over 6, it's going to be negative sine of 5 pi over 6. And so again, I got to think about the related angle, and we're still in quadrant 2. Now sine is positive in quadrant 2, so the expression here is already negative. And again, if I remember that cosine of pi by 3 is a half, sine of pi by 6 is a half. I don't know, that's just how I do it, right? You can do special triangles and all this stuff, but if you're doing these often enough and you remember this from MHF, you want to memorize these as much as you can. But you can also use your calculator to evaluate these if you have to. So what does this mean? Y prime, when x is 5 pi over 6, y prime is negative a half, so that means our slope is negative 1/2. You need to state that, by the way. State m equals like as slope, or write slope equals or something like that. Okay, now I got everything I need for to use this formula. Right? That was the whole point, is I needed the input. So the output of this formula is the equation. So y minus y1, so plus root 3 over 2 equals m, which is negative 1 over 2, x minus 5 pi over 6. I'm going to multiply both sides by 2, multiply the whole thing by 2. I saw this on, I believe, the test and the quiz and some of the learning goals and stuff that we did over the last little while, that people are doing things like this. F at x equals, so this is a sidebar here, 1/2, let's say it was something like x squared plus 3x. And they multiply through by 2. But you can't do that. Or this was probably f prime x. Why can't I do that here? Yeah, that would give me 2. Like, you're multiplying both sides. So it would get rid of that. But I'd have a 2 on the other side. You can do that when it's equal to 0. When I have an equation, not when I have a function like that. You can't just multiply the function by 2. But it's funny how, like, that's pretty obvious when it gets pointed out, but that's something that I've seen a few people do over the last little while. So don't do that. Be very careful. But in this case, we can. So 2y plus root 3, and I'm left with negative 1 times the bracket, so I'm going to distribute that through equals negative x plus 5 pi over 6. And I'm going to put this in standard form. So I'm going to bring the x over, x plus 2y plus root 3 minus 5 pi over 6 equals 0. And I'm going to leave those as exact values, not try to put them together. Kind of nasty because of the pi in there, but. Any questions about that? If you ever asked about the equation of a tangent line, or remember sometimes we give you the slope of the tangent, you have to find the point, or like there's all different kinds of ways that you can do this. But think about what you're given, think about the formulas that you might use if you're finding the equation, and what's the input, what's the output. That can be a really good problem-solving technique. Okay, I want you to try this one, get it started on your own at least. It's the same idea, it's the same question from above, which was find the equation of each described tangent line. So we're finding the equation of this when x equals pi over 4. So cos squared x plus tan x. So when I evaluate to find the y value when x is pi over 4, cos of pi over 4, all squared. I'm used to rationalizing denominators, so to me, cosine and sine of pi by 4 are root 2 over 2, but you might have them as 1 over root 2, and either way it really works out to being very similar math. It's like this step is different, but the next step is kind of the same anyway. So if you do it the other way, and in fact, if you did do it the other way, which I hope many people did, you'll see that it obviously works out the same. Okay, and so this is kind of nice when I square it because that goes away, so I get 2 over 4 plus 1. And if you had 1 over root 2 all squared, you'd have a half. 2 over 4 is the same as a half. So a half plus 1 is 3/2, so 3/2. Okay, lots of people started with that and got that so far. Hopefully you've done this part as well, where you have to take the derivative to find the slope. If you haven't, well, I guess I just blew it for you, but there you go. So now why don't you try to evaluate it if you haven't done this part yet. Find the slope of the tangent at pi/4. Okay, we're running out of time here, so I'm going to try to wrap this up. Secant squared pi/4. Now, there's different ways of doing this. So you have to come up with your way that you like to do it and you like to see it. This is the reciprocal of cosine. So cosine is 1/√2. So the reciprocal of that is just √2. That's probably the easiest way to think about it. So this is √2 all squared. Isn't that right? And then I'm going to clean some of this stuff up. So 2 divided by 2, those are gone. And I get negative. √2 times √2 is 2. So negative 2/2 plus 2, which is 1. So the slope is 1. I've got the x value. I've got the y value. I can now use this formula. Y minus 3/2 equals 1, which I don't really need, times x minus pi/4. So I'm going to move everything to one side, and I get 0 equals x minus y plus 3/2 minus pi/4. Technically, we're not supposed to have fractions, although fractions in terms of pi is a little bit different. But let's multiply the whole thing through by 4 to get rid of all the fractions. So I end up with 4x minus 4y plus 6 minus pi equals 0. And that is proper standard form with no fractions. Any questions? What do you think about that? Here's your practice.